Hello friends, welcome back to my YouTube channel. In this class, I am going to discuss some previous year questions, that is PYQs of GATE, which are based upon the concept of entropy. You know, this chapter of entropy is a very important chapter insofar as the GATE exam is concerned. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. Let's get started. So this question was asked in GATE 2010 and it carries 2 marks. The question is like this. Consider the following two processes. First process is a heat source at 1200 Kelvin lodges 2500 kilojoule of heat to a sink at 800 Kelvin. And second process is a heat source at 800 Kelvin lodges 2000 kilojoule of heat to a sink at 500 Kelvin. Which of the following statements is true? Option A is process 1 is more irreversible than process 2. Option B is process 2 is more irreversible than process 1. Option C is irreversibility associated in both the processes are equal. And option D is both the processes are reversible. So, irreversibility of a process is decided by a path function which is entropy generation. The more the entropy generation in a process, the more irreversible the process is. And in case of reversible process, entropy generation is 0. In case of a reversible process, entropy generation is 0. And in case of an isolated system, entropy generation is same as delta S of universe. These things I have already discussed in my earlier lectures. Whenever you are to consider, you are to determine the degree of irreversibility of any process, first you must try to find out entropy generation that takes place during that process. And how can you calculate entropy generation? You can do it by calculating delta S of universe. Universe means system and its surroundings can be together considered as a universe, and it is always an isolated system. So first thing we must do, we must find out the entropy generation or delta S of universe. Delta S of universe means the change in entropy of universe, that is the system and surrounding, that has occurred during the process. And there are two processes given in the question, and we will calculate entropy generation or a delta S universe of both these processes. And the process with more delta S universe value, of course both will be positive because both these processes are irreversible. And there is no question of delta S universe coming to be 0 because both are irreversible. If you see, because there is a heat transfer due to finite temperature difference in both the cases, process 1 and process 2. Whenever heat transfer takes place through finite temperature difference, that is an irreversible process. So we have to determine the extent of irreversibility of both the processes. The more the entropy generation value or delta S of universe value, change in entropy of universe, the more irreversible the process is. So first find out. So if you go to calculate delta S universe of process 1, suppose heat source is at temperature 1200 Kelvin. 1200 Kelvin heat source, and it lodges this amount of heat that is transferred by this source is 2500 kilojoule. So this heat that flows out of the source is 2500 kilojoule, and it goes directly to a sink, which the temperature of which is 500 Kelvin. So temperature the temperature of source is 1200 Kelvin and temperature of sink is 500 Kelvin, and heat is transferred from source to sink, and that heat is 2500 kilojoule. So first we must calculate the delta S of this source and delta S of sink, and of course delta S of rod that connects these two reservoirs. And if you consider this whole system as an isolated system, this is the boundary of this isolated system, and so first we must calculate delta S of source, this is delta S of sink, and delta S of this rod. These three are the parts of the universe. If you consider this as a universe or isolated system, then it consists of three parts. First one is the source, then is sink, and this rod. So first we will calculate delta S of source, and it is equal to this temperature. No matter whatever heat flows out of this reservoir, its temperature does not decrease. That's why it is called a reservoir. So what is the delta S of this source during this process? Minus of 2500 divided by 1200 kilojoule per Kelvin. And you see why minus sign is put? Because the heat is transferred from this source. Heat is going away from this source. And if you calculate delta S of sink, the same heat enters into the sink without causing any increase in the temperature of this reservoir. So this is plus 2500 divided by 5, this temperature is 800. 12,000 Kelvin is source temperature and 800 Kelvin is sink temperature. In second case, sink temperature is 500 Kelvin. So this is 800 Kelvin. So this is 800 and kilojoule per Kelvin. But if you consider delta S of rod, it is equal to 0, because once this has attained steady state means there will be no change in entropy during this rod. So delta S of universe, or which is same as entropy generation that has occurred during the whole process, is delta S of source plus delta S of sink. That becomes 2500 divided by 800 minus 2500 divided by 1200 kilojoule per Kelvin. This is equal to 1.041 kilojoule per kg, kilojoule per Kelvin, in fact, change in entropy of universe, and this is also equal to entropy generation during the process. And if you want to calculate the change in entropy of universe or entropy generation during the process 2, if you calculate the change in entropy of universe during the process 2, this is same as entropy generation during the process 2. It will be, the source temperature in the second case is 800 Kelvin. This temperature is 800 Kelvin. And this heat that is transferred is 2000 kilojoule and sink temperature is 500 Kelvin. 500 Kelvin. So, if this is considered as an isolated system or your universe, then we are to calculate delta S of universe, which will be same as entropy generation during the process. So, entropy generation is a path function that will differ from process to process. This is not a property. You know, in thermodynamics, there are three path functions. One is heat, second one is work, and third one is entropy generation. So, this is during the process 2 is delta S of universe during process 2. So, in this case, what will be delta S of universe? So, delta S of source is equal to minus 2000 divided by 800 kilojoule per Kelvin plus, and this is the delta S source. Delta S of sink will be plus 2000 because the heat is going to the sink and heat is being transferred from the source, kilojoule per Kelvin, and delta S of rod is also 0. So now delta S of universe will be delta S of source plus delta S of sink. So 2000 divided by 500 minus 2000 divided by 800 kilojoule per Kelvin. So this is equal to 2000 1 upon 500 minus 1 upon 800 kilojoule per Kelvin. So this is equal to 2000 multiplied by 8 minus 5. This is equal to 3 by 2, that is 1.5 kilojoule per Kelvin. This is the entropy generation during the process 2. Process 2. So 1.5 kilojoule per Kelvin. And in case of process 1, we had already calculated the entropy generation is 1.041 kilojoule per Kelvin. Both are positive. Both are positive. During process 1, entropy generation was 1.041, and in case of second process, this is 1.5 kilojoule per Kelvin. So this is the higher value. So more entropy is generated during the second process. Both processes are irreversible, and second process is more irreversible than first process just because its entropy generation is higher than that of process 1. Entropy generation is nothing but the change in entropy of universe, and change in entropy of universe is nothing but the summation of change in entropy of system and surrounding. So next question, that is, you see, this was again asked in the GATE 2010 and it carries 1 mark. You see, 1 kilogram of water at room temperature is brought into contact with a high temperature thermal reservoir. The entropy change of the universe is option A equal to entropy change of the reservoir, equal to entropy change of water, equal to 0, and option D is always positive. You see, whenever there is a heat transfer through finite temperature difference, heat transfer through finite temperature difference is always an irreversible process. In this case, the heat transfer takes place through finite temperature difference. Suppose temperature of body is 60 degrees Celsius and another body, temperature of another body is 30 degrees Celsius. This is a finite temperature difference. If heat flows from this body to this body, obviously it will be an irreversible process. Suppose the temperature of body is 30 degrees Celsius and temperature of another body is 30.002 degrees Celsius, and if heat flows from this body to this body, this may be a case of reversible process, because here heat transfer takes place through infinitesimal temperature difference. Temperature difference is quite small in this case, but this is a case of finite temperature difference. Heat flow transfer through finite temperature difference, because water at room temperature is brought into contact with a high temperature thermal reservoir. In place of this, if that 1 kg of water has come in contact with a large number of reservoirs through some infinitesimal temperature difference, one after the other, to attain the final temperature, then it would have been a case of reversible process. But here 1 kg of water directly comes into contact with a high temperature with thermal reservoir. So this is a case of irreversible process. And according to principle of increase of entropy, delta S of universe is greater than 0 for irreversible process. Irreversible process. That means change in entropy of universe will be always positive for an irreversible process. And since this is an irreversible process, so delta S universe is going to be positive. Had it been a reversible process, delta S universe would have been 0. So the option D would be the correct answer. Delta S of universe, change in entropy. Entropy change of the universe is nothing but delta S universe. It will be always positive. So option D is the correct answer. Question number 3. You see, an amount of 100 kilowatt of heat is transferred through a wall in steady state. One side of the wall is maintained at 127 degrees Celsius and the other side at 27 degrees Celsius. The entropy generated in watt per Kelvin due to the heat transfer through the wall is, you have to calculate. And it was asked in 2014, 2 marks, and it was asked in set 3. You see, here this is a case of conduction of heat through wall. Heat is flowing through this wall. So suppose Q is the amount of heat that flows through this wall, and this temperature is 400 Kelvin, because 127 degrees Celsius in terms of Kelvin, that will be 400 Kelvin. This temperature is, and this side of the wall is at a temperature of 27 degrees Celsius. That means 300 Kelvin. 27 degrees Celsius or 300 Kelvin. So TH suppose 400 Kelvin and TL is suppose 300 Kelvin. And the amount of heat that flows through this wall is 100 kilowatt. Q dot is rate of heat flow through this wall is 100 kilowatt. We have to find out entropy generated. Whenever heat transfer takes place through finite temperature difference, means this is an irreversible process, and entropy is generated only during an irreversible process, and there will be some entropy generated and it will be positive value, that's to be sure. But what is that value? So if you apply entropy balance principle, entropy balance principle is like this. Entropy balance principle is S dot in minus S dot out plus S dot generation is equal to delta S of system. S dot in means rate of entropy that is transferred into the system, and S dot out means rate of entropy that is transferred out of the system, and rate of entropy generation. Entropy is generated during the system, during this wall, just because it is an irreversible process. Had this been a reversible process, there would be no entropy generation. So whatever S dot in minus S dot out is net entropy transfer into the system. And entropy is transferred along with heat or mass, but in this case there is no mass transfer, only heat transfer is there. So with heat transfer, here an entropy is entering into the system, and here entropy is leaving the system. So that is the S in will be there, S out will be there. S generation, rate of entropy generation, we are to calculate. Delta S system in this case is 0, change in entropy, because in the question you see it has been written that it is in steady state. So in steady state, no property changes with respect to time. Since we are calculating rate of change of entropy, in case of steady state, properties don't vary with respect to time. So in this case, entropy is a property of system, so delta S dot will be 0. So this is 0. So from this equation we can calculate rate of entropy generation. So S dot in will be, what is the entropy transfer into this wall? So that is heat divided by temperature at which the heat transfer takes place. So here heat that is coming into the system is, that is 100 kilowatt. 100 kilowatt divided by temperature is TH is 400 Kelvin, minus the same heat also flows out of this wall, that is 100 kilowatt divided by 300 Kelvin plus S gen is equal to 0. On equating this, entropy, rate of entropy generation will be 100 by 300 minus 100 by 400 kilowatt Kelvin, kilowatt per Kelvin. But it is required to be, answer is required to be found out in terms of watt per Kelvin. Watt per entropy generation has to be calculated in terms of watt per Kelvin. So you have to multiply this by 1000 to find out the answer in terms of watt per Kelvin. 100 taking common, 1 by 300 minus 1 by 400 multiplied by 1000 watt per Kelvin. So this comes out to be 1000 divided by 12, that is 83.33 watt per Kelvin. So answer would be 83 point, this is the answer, 83.33 watt per Kelvin. So 83.33. So this is your entropy balance principle. Entropy change can take place through net entropy transfer and plus net entropy generation. एंट्रोपी ट्रांसफर होता है, नहीं तो एंट्रोपी अंदर में कुछ जनरेशन भी हो सकता है, लेकिन एनर्जी जनरेशन नहीं होता है. दैट इज द डिफरेंस बिटवीन एंट्रोपी बैलेंस एंड एनर्जी बैलेंस प्रिंसिपल. Had it been an energy balance principle, it would have been E dot in minus E dot out, and this E dot generation term is not there. Energy is not generated, but entropy is generated, and delta E of course would have been the right hand side term. So next question is 1 kg of an ideal gas. 1 kg of an ideal gas whose gas constant is given to be R is equal to 400 joule per kg Kelvin, and the specific heat at constant volume is also given 1000 joule per kg Kelvin, at 1 bar and 300 Kelvin is contained in a sealed rigid cylinder. During an adiabatic process, 100 kilojoule of work is done on the system by stirrer. The increase in entropy of the system पूछा है. Increase in entropy. Suppose some ideal gas, 1 kg of an ideal gas is contained in a sealed rigid cylinder and it is also insulated, because it is given that during an adiabatic process, so some stirring work is supplied. Paddle wheel work is supplied to this. Paddle wheel work is a work input to the system. So this is a rigid container, rigid cylinder, and it is of course insulated, because in adiabatic process 100 kilojoule of, so mass, what are the data given? Mass is 1 kg, R is 400 joule per kg Kelvin, this is characteristic gas constant, and Cv of course is given 1000 joule per kg Kelvin. And initial temperature of gas is 300 Kelvin, and the pressure of gas is of course 100 kilopascal. And work that is done on this system, or that is input to the system, stirring work, is 100 kilojoule. This is the work done on the system. If you go by the convention, this is work done on the system. So we have to find out what is the change in or increase in entropy of the system. You see, if you apply the energy balance principle, this can be done by two ways. Once you can find out the final temperature or final volume, what is the change in entropy of ideal gas. The formula is there, like there are two formula for finding out change in entropy of ideal gas, that is like mCv ln Tf by Ti. Tf is the final temperature of ideal gas, Ti is the initial temperature of ideal gas, plus Mr ln Vf divided by, sorry, this is capital Vf, Vf by Vi. This formula can be used, or in terms of Cp terms also, and in pressure terms also equation can be written. So this is the, in fact, the basic formula to find out the entropy change of ideal gas. So we must know what is the final temperature, because Vf here is same as Vi. So this term would be eliminated. Because this is given that this is a rigid cylinder. So volume will not change. Vf is equal to Vi, and this term would be 1, and ln of 1, natural logarithm of 1 is 0. So this term will be 0. So once you can find out this term, M is given, Cv is given, only Ti is also given, you have to find out the final temperature. Just after the stirring work has been supplied, what is the increase in temperature and what will be the final temperature of this ideal gas. Once you are able to find out Tf, your problem would be solved. So this was asked in the 2017 and it carries 2 marks. This was asked in the 2017 and it carries 2 marks, and it was asked in the set 1. You see, for that we have to find out Tf only. So this can be done by two methods. One is energy balance, energy balance principle अप्लाई करने से हो सकता है, नहीं तो फर्स्ट लॉ का जो इक्वेशन है Q इज इक्वल टू डेल्टा E प्लस डब्ल्यू और डेल्टा U प्लस डब्ल्यू, दैट इक्वेशन को अप्लाई करने से भी हो सकता है. सो इफ यू अप्लाई एनर्जी बैलेंस प्रिंसिपल, दैट इज नथिंग बट E in minus E out is equal to delta E. In fact, this is delta E, since there is no change in kinetic energy and no change in potential energy, we can write delta U in place of delta E. Otherwise, the general principle is the delta E, change in total energy of the system. E in is the energy that is entering into the system during the process, and E out is the energy that leaves the system during process, and net energy that is transferred into the system goes on to increase the energy of the system. And if these delta E and delta EP terms are negligible, then it will go on to increase the molecular internal energy of the system. This is what has been written in this equation. So here you see no energy is leaving the system. You see here only steering work is always paddle wheel work, or steering work is a work input. Steering work is a work input. So energy is entering into the system in form of work only, and no energy is leaving because this is an adiabatic container, adiabatic cylinder. So no heat is neither leaving nor any heat is entering into this cylinder. That's why whenever energy is entering into the system, its temperature of gas is increasing. And since this is rigid also, there is no displacement work or boundary work is also not there. So E out is 0. E in is nothing but your 100 kilojoule in form of pedal wheel work. 100 into 1000 joule is equal to, for delta U we can write mCb delta T. mCb delta T. This is equal to mass of ideal gas is 1 and Cb is 1000 joule per kg Kelvin multiplied by delta T. On equating this, delta T is 100 डिग्री सेल्सियस हो सकता है और केल्विन भी हो सकता है. डेल्टा टी will remain same whether you express it in terms of degree Celsius or in Kelvin. So since delta T is 100 Kelvin and initial temperature of ideal gas is 100 Kelvin, initial temperature of ideal gas is 300 Kelvin. That means delta T means Tf minus Ti is equal to 100 Kelvin, and Ti is given to be 300 Kelvin. So Tf will be 100 plus 300, that is 400 Kelvin. Final temperature of ideal gas is 400 Kelvin. This can be determined by energy balance principle, applying energy balance principle, or else we can use also alternatively, we can also use the usual first law equation, that is Q is equal to delta E plus W, or when the delta E and delta EP terms are neglected, this becomes delta U plus W. Q is the heat input into the system during the process, W is the work done by the system during the process, and delta U is the change in molecular internal energy of the system. So you see here no heat enters into the system. So as far as Q is concerned, if you use this equation, Q will be 0. So delta U, but W here will assume negative value because in the original equation W was for work done by the system, but in this case steering work is a work that is done on the system, and by convention work done by the system is positive and work done on the system is negative, and this work is an input to the system. When work is done on the system, it is taken to be negative. Originally this equation has been written for Q to be positive, W to be positive. Of course heat has to be transferred to the system and work is transferred from the system, but here work is transferred to the system. That's why we have to put minus sign, minus 100 kilojoule, but in terms of joule this will be 100 into 1000 joule. So from this delta U will be 100 joule, 1 lakh joule. So delta U is nothing but mCv delta T is equal to this much. M, in place of M I will write 1 kg means 1 into 1000 into delta T is equal to joule, from which delta T is nothing but 100 Kelvin. So Tf again would be 300 plus 100, that is 400 Kelvin. So this can be, final temperature can be determined either by using energy balance principle or by using the first law equation that is applied to a closed system for undergoing any process. This equation is the first law equation applied to a closed system undergoing any process, and this equation is Q is equal to delta E plus W, or in case of a stationary system that this equation reduces to delta U plus W, where delta Ek and delta Ep terms are neglected, where Q is the heat supplied to the system and W is the work done by the system. So once the TF is determined, we can apply this equation, that is change in entropy, that is used for ideal gas. That will be delta S will be mCV ln TF upon Ti. Since no change in volume is there, so right, and this term will be eliminated, because it is given in the question that this is a rigid cylinder. In case of a rigid cylinder, there will be no change in volume. This is equal to 1 into 1000 multiplied by ln 400 divided by 300. This is equal to 287.682 joule per Kelvin. 287.682 joule per Kelvin is the change in entropy of ideal gas during the process. Change in entropy of system, and though here no heat is supplied, the entropy will increase. So that is a basic concept behind this problem, that you should not think that no heat is transferred, so entropy change will not be there. But since the paddle wheel work is being supplied to the system, stirring work is supplied to the system, entropy also increase, just because this is an adiabatic process, so temperature would also rise, and the change in entropy of the system will be, change in entropy of ideal gas would be 287.682 joule per Kelvin. It was asked in the 2017 and it carries 2 marks. So thanks for watching.